Y'all, today we are continuing our discussion of acceleration. Hopefully you watched the first video, the average acceleration video, where we talked about what acceleration was, and that is a change in velocity. So I'm going to write the shorthand version of the equation, change in velocity over time. Well, maybe you remember from Unit 1 that velocity is a vector, which means it includes direction in the measurement. I'm going to draw the little vector symbol right here so you can kind of know what that is and remember. You don't need to remember it. I'm just showing you. Maybe you remember the equation for velocity. Now it seems like a long time ago. Velocity equals delta x over time. Delta x was displacement, and it also included direction. So since this value included a direction, that made velocity a vector as well. But since acceleration has velocity as part of its equation, acceleration is also a vector and also has a direction. Now, some of you are probably wondering, how could I change someone's velocity in the negative direction or in the positive direction? Maybe that doesn't quite click for you. How can I have an acceleration forwards or backwards? Well, you can speed up, you can slow down, you could also literally change direction is a type of acceleration, which involves direction. Or let me do a silly, cheesy example right here. But some of you are learning how to drive, or maybe you're asking questions about how other people drive or not. How do you make your car accelerate? How do you make your car go faster? Some of you are screaming internally, press the accelerator. Duh, that's why it's called that. My big concern here is not the word accelerator or gas pedal. You are pressing on it. You are applying a force. We will learn in a later unit that all accelerations, all changes in motion are caused by a force. And they are directly related to that force causing the change. So it might be hard for you to picture changing your velocity in a certain direction, but you can definitely picture a force. I can apply a force forward or pull you backward. I can apply a force in a direction. Well, the change or the acceleration is always going to be in that same direction. So whenever you're thinking about the direction of the acceleration, think about the direction of the force, in the direction of the force. Okay? So, as a for instance, we got person A, and they are walking this direction. So that means they have a positive velocity because we are going to say to the right is the positive direction, just like we do in math class. So we're going to call this person A. Person B wants person A to go faster, wants person A to move away from them more quickly. Which direction would person B push or pull person A to make them go faster? Well, maybe that's common sense, but you would push person A in the same direction, right? To make them go faster. Well, that push is a force, which means I am also accelerating that person in the same direction, which would make that a positive acceleration. So this would make them go faster. Or we can say speed up. I'm going to use SU for short. Oh, you can't see that. Go faster or speed up, but you get the idea. So now let's say we want the exact opposite to happen. This person is trying to get away from us and we are trying to slow them down. We are trying to make sure person A does not get away from person B. Which direction would I push or pull person A to make sure that they slow down? Well, I would pull them backwards, right? To slow them down. If they are moving in one direction and I want to make them start to slow down, I would actually apply a force backwards, which, again, maybe you remember from math class, this is the negative direction. So that means the person is experiencing a negative acceleration, a negative change in velocity, which means they are slowing down. Now be careful here. I don't want you to get comfy with the idea that negative acceleration is always slowing down and positive acceleration is always speeding up? Because that is absolutely not the case. Let's flip the situation. I'll use different colors. Let's say person B is now traveling this direction, which means they have a negative velocity. How would person A slow down person B? Well, they would pull them in the opposite direction, which means they would experience a positive change, which means they would slow down. All that negative and positive mean are a direction. Which direction am I pushing or pulling, or which direction am I moving? I can move in one direction and be pushed or pulled in the same or opposite direction. They're just directions. They don't always mean slowing down or speeding up. But I do have a trick for you. You're going to notice in this picture right here, the acceleration and velocity are in opposite directions, and that person is slowing down. In the second example, velocity, motion is in this direction, and acceleration is in the opposite direction. This is also an example where they are both slowing down. If person A had pushed person B in the same negative direction, that person would speed up in the negative direction. Okay? So just something to keep in mind, whenever those signs are working against each other, that means the object is going to slow down. Whenever they're both in the same direction or have the same sign, that means whatever the object is doing, it's going to speed up in that same direction that it's moving in. Could be negative, could be positive. So in your notes, and then right here, I have this handy little chart. You can't see the bottom part because my face is in here, but I will move it for you in a minute. The more important stuff is on top anyways. This is just showing you if my velocity is a certain sign compared to my acceleration, what is the object going to be doing? So when they're both positive, they're going to be speeding up. And I'm going to even go so far as to say they're going to be speeding up in the positive direction. Remember, velocity's sign is only positive or negative because it's telling me what direction it's moving in, either in the positive or the negative direction. So when both of them are negative, that means it's speeding up in the negative direction. Look at that. No matter what the signs are, if they're opposite, they're slowing down. The difference is, again, direction. If I have a positive velocity, I'm slowing down while moving in the positive direction, or I'm slowing down while moving in the negative direction. Direction always depends on velocity. That tells me what direction I'm moving in. The last little bit of the chart that I'll show you from behind my face. This is just telling me, and I'll kind of rewrite the letters right here so we don't have to keep going back and forth. If I have a velocity, positive or negative, but I have no acceleration, acceleration means a change in velocity, right? If I have no change, that means I'm moving at a constant speed, not changing, it's staying the same. So, is it possible for me to not be moving and be accelerating? Yes. I hate this phrase, speeding up from rest. It technically is true, but this would also be an instance of potentially just changing direction. I like to compare this to maybe suicides in gym class. Have you ever done a suicide before where you have to like run one way, stop, pivot, go the other way, and kind of keep doing that? Very briefly, when you are down on the ground and you are pivoting, you are at rest. Does it really feel like you're at rest? You are still applying a force on your body. You are still accelerating. You are still changing because you're changing the direction yourself, even though you're briefly at rest. So this could also be an example of changing direction. Both are true, but I like changing direction better. And then if I'm not moving and I'm not accelerating, I'm just sitting there. I'm just sitting still. Cool. Now that we've got all that down, I have a scary slide for you. I don't want to scare you guys too much or even use that word because I don't want to freak you out, but we are going to talk about uniform acceleration. Now, that is only a little different from average acceleration. Average acceleration is just kind of explaining to you what acceleration is. It's average the whole acceleration over the whole trip. In this class, we are going to deal with unchanging acceleration. We are going to assume objects are staying at the same acceleration the entire time. So uniform means the same, not changing. So lucky us, we are not ever going to be dealing with changing accelerations. Velocity will change because that's what acceleration is, but the acceleration will stay the same. I keep saying that, but you get the idea. So I can use all 4 of these equations right here anytime I am solving a problem where an object is moving with a constant acceleration. They are not changing how much they are slowing down or speeding up. Okay? So that top equation should maybe look a bit familiar. I'll kind of write it out. The average acceleration, red was a poor choice. The average acceleration of an object can be calculated by using this equation. And I'll write it in a different color, slightly different color. You can see if I rearrange this equation, that this equation right here is the same as this equation right here. That is the average acceleration equation, just rearranged differently. You solved for final velocity instead of initial velocity, or instead of acceleration. So that equation should at least be familiar to you, that top one. The rest have squareds, have halves, they're just different looking equations. So these are all of the equations you could use. Some people have issues picking out which equation is the right equation to use when solving a word problem. So I'm going to teach you a trick or two to help you figure that out. First, take note that all of these equations are made of the same 5 letters. Each equation only has 4 of those letters, but they're all made of the same 5. We have delta x, we have acceleration, we have time, and since acceleration is a change in velocity, we have final velocity and initial velocity. We could have lots of different types of velocities, not just 2 whenever I'm accelerating, right? Because that is a change in velocity, so just kind of keep that in mind. But all 5 of those equations don't have any different letters other than those 5. All 4 of those equations have those 5 letters. So that means since each of those equations only has 4 of those letters in it, each one of those equations is missing 1. Let's go through and figure that out. First equation, kind of obvious because it's right here. First equation does not have delta x in that equation. Next equation does not have time. No time in that equation. Next equation is missing final velocity. They have initial velocity, just not final. And then that last equation has no acceleration in it, none. So this will actually help us when picking out an equation. I have a couple of different methods for you. You might not like either, you might only like one. You should pick the method that works the best for you. But it would be smart to maybe mark next to the equations in your notes, or on your formula sheet if you want to write on it, which equations are missing which variable. So here is a strategy. Problem solving strategy, you should always list your givens or what the problem tells you. Okay? The next one says you should list your unknown. What are you looking for? We'll say solving for. What are you solving for? Figure out which variable is completely missing. Basically, which one was not talked about. Or mentioned. And then you can pick an equation based off of that. That's what this last bottom part says. So when we're reading a problem, maybe they talk about an object that is accelerating, but they don't say how long it takes to accelerate. They don't ask you to solve for time. They don't mention time at all. Then I would pick the equation without time in it because I don't care about time in this particular problem. Cool. Let's do an example problem. How long would it take for a sled to come to a complete stop if it was moving at 18 meters per second initially and decelerating at a rate of 4.3 meters per second squared? I like to go through and identify pieces of information that seem important. So, for instance, how long would it take? That is a time, except they didn't tell us time. They are asking us to solve for time. So that's my question mark. And I know that seems silly to write down. Trust me, it will help when you're picking out an equation. Please take note of it. So how long would it take for a sled to come to a stop? This is talking about the motion of the object, so it is going to be important here. If it was moving at 18 meters per second initially and decelerating at a rate of 4.3, this should say meters per second squared. I know it's written kind of funny. So it's moving at 18 meters per second initially. Well, that one's kind of obvious. That is its initial velocity. It even says initially right there. Some of you are going to be tempted to label this next number your final velocity, but it has different units. Meters per second and meters per second squared are not the same. And in fact, maybe you learned from the last video, meters per second squared are a dead giveaway that is acceleration. This problem also says it's decelerating, which is a type of acceleration, right? So let's go ahead and write stuff down. Time is what we're looking for. Initial velocity is 18 meters per second. And we can assume that's positive since they don't specifically say it's negative. But it's decelerating, which means it's slowing down. And we learned earlier, if it's slowing down, that means the acceleration has to be in the opposite direction as the velocity. So I am going to make this a negative 4.3 meters per second squared. Now, all of my equations have 4 pieces of information. I'm either missing one or forgetting one. I'm forgetting one. That one piece of information I circled. How long would it take to come to a stop? I can assume from that the final velocity is 0. Great! Which of my 5 letters, and I can write them all for you again right here, which one of these letters was not mentioned in this problem? We're not solving for it. We are not finding it. We are not told anything about this variable. That's delta x. So we don't care about delta x, so I am going to pick the equation without delta x in it, which is that first one. Okay? I'm going to tell you something really quickly. Here is what I hate about this method. Is some of you will make this mistake, and please don't do it. Oh, I don't have time. So I'm going to pick the equation without time in it. Let me ask you this. If you're solving for time, if they're asking you to find the time, how am I ever going to find it if time is not in the equation? So just be careful. Think about that whenever you're using this method. Like I said, I personally don't like that method. I like where I just pick the equation that has everything I need and what I'm looking for. But that's a trick for those of you who struggle with doing that. So now, hopefully from here, it's super easy. You just plug in stuff and just rearrange and solve. So final velocity is 0. Initial velocity is 18 meters per second plus negative 4.3 meters per second squared times my time. So now I rearrange, take it step by step, and I can maybe move my little face. See if I can do this. Ooh, it's blocking some of my information, but you can see at least the rest of my work. Be careful here with your algebra. I know some of you struggle with algebra, so I'll take it step by step. I shouldn't separate these two yet because they're being multiplied together. To get rid of it, I need to divide, which you could do, but you would have to divide by every little piece of the equation. Make everything shorter and smaller where you can. 18 meters per second is not attached to anything except by an addition sign, so I can just subtract that and move that over here. Now pay attention. I know my face is kind of blocking it, but there is a negative right there. I'll write it lower so you can see it. There is a negative 18 right there. So when you write this, I'll scooch it over a little bit. There we go. 18 meters per second. That goes away. It becomes 0 equals negative 4.3 meters per second squared times my time. Now super easy. I divide by 4.3 on both sides. Oh my gosh, look at that. My negatives cancel. Beautiful. If I had forgotten my negative, I would have gotten a negative for time. And that's bad news. I should never, that's one way I can check myself, is I should never get a negative time because I am never going to go backwards in time, at least not in this class. So the time I got was 4.186, but if I'm rounding to proper sig figs, 4.2 seconds. And I think in the PowerPoint that's posted online, the answer should be on here. Great. I will do, oh, there it is, right there at the bottom. Way to check yourself. It's behind my face again. My face is just in the way a lot. All right, so let's try another one. A plane is driving at 5 meters per second. Initially, ooh, I can probably label that initial velocity, then speeds up to 32 meters per second. Since that's my next velocity, I'm just going to go ahead and make that final. I don't know if that's the actual final, but it will be for my equation since that's the part of the motion I'm ending with. Over a distance of 250 meters. I know it says distance, but distance and displacement are so similar, especially when they're all moving in the same direction and there's no direction change. They will be the same. So I'm going to label that displacement. It has a uniform acceleration, which is just telling me the acceleration stays the same the whole time. What is it? That's kind of what they're asking for. So again, I'm going to write out everything I know. If they don't specify a direction, assume positive. Delta x is 250 meters, and acceleration is my question mark. The one letter we haven't talked about this problem is time. So I'm going to look at my formula sheet that I'm getting further and further away from. Hey, look at that. I already circled it. There's the equation without time in it. So my next tip for you is to be sure to copy the equation down correctly first. I see so many people make the mistake of copying down half of one equation and half of the other, and then, or forgetting a squared or something, and so then they don't get the answer right even though they plugged everything in correctly because they didn't have the formula or the equation written down correctly. So now I have 32 meters per second, and for those of you who struggle with math, don't feel like you have to write the units in every time, but never leave off a negative or positive if it's specified, because that will mess with your answer. So we are looking for A, so I'm going to leave that A in the equation, and then times 250. So take it one step at a time. 32 squared is 1024. And if you want to, keep track of the units, but if they all work out perfectly, you'll end up with the units you need for acceleration. So your call. Equals 25 plus, I'm going to go ahead and multiply 2 times 250. Just again, each time I want to simplify, each time I want to make this equation look easier. So 2 times 250 is 500 times A. Again, please don't just add those two together. This is stuck here, so I can't just add it to anything. It's stuck with that A, but I can subtract 25 from both sides. And I end up with 999 equals 500A. And then if I divide both sides by 500, I get that A is 1.998, but I should still be rounding to proper sig figs, so I'm not going to write my units yet. And all of my numbers up here look like they have 2 sig figs, even this one. So I'm going to round to 2 sig figs, which I wouldn't just write 1.9 because this digit right here is telling me to round up. So I would round to 2.0 meters per second squared. It's speeding up, so I should have a positive acceleration. That makes sense. Check your numbers to make sure they make sense before you move on. Great. I am going to do the last example and then move on. So you can check yourself. I can work these out in another video if you want. I'm actually just going to end this video because it's already running long. You can watch the next examples in the next video if you would like.